I think we should probably get started. So I don't know if you guys have been in the other chess timer talk. I'm just going to explain how it works real quick and then give it to Simon. But the way that this whole chess timer format is supposed to work is supposed to put a little bit of pressure on the audience to interact with the speaker. So he is limited to only 20 minutes of speaking time. And you guys have to speak the other 20 minutes of this slot. So if you guys are just sitting here and sleeping through his presentation, you're not doing the chess timer thing correctly. You're a part of this, okay? So it's up to you to, like, focus and try to come up with some good questions to ask him. He might be sneaking stuff in where he leaves a big hole, and you guys have to, okay, well, hey, you didn't explain that thing. Can you go into a little bit more detail about that? That's a valid thing to raise your hand and ask. The only rule is that you can't ask him questions for the first 5 minutes, because he's got to start somehow. You can't just drill him the first 30 seconds. So wait 5 minutes before you ask questions. The chess timer is right here. It's this little black thing. I'm not sure how many people can actually see it. Maybe Torsten has to like wave it around every now and then. But there's one thing to note about this chess timer. Speaker and audience have only 20 minutes. The chess timer, unfortunately, only operates in 25-minute chunks. So if you look at the time, subtract 5 minutes. I'm really sorry about this. So do a little bit of arithmetic when you look at the chess timer. But that's it. So please, please, please help him out. Ask questions, get involved, and don't really be afraid. If he leaves something unresolved or not clear, maybe that's like deliberate. Maybe you're supposed to raise your hand and ask. So be on the offensive and ask questions. But I'm going to let Simon start. So. Second chess timer of the day, thank you.
Okay, thanks, Heather. Hi, I'm Simon. I lead the data department, data science department at GoOpti. So very briefly, what we do, we are an on-demand shared transport service. You can think of us sort of like Uber Pool, except we focus on airport transfers on longer distances. So we try to pack as many people into a van and then send that van 200 kilometers out to some airport. So basically, the core of what we do is very intimately tied with working with data. The three core things my department does is we do routing, we do packing, meaning how can we pack as many people as possible into one van, and we do demand projections, or rather risk management. So those things are in various ways tied with data, and this talk, and before that, I worked as a consultant doing data science and helping companies become data-driven. So this talk is going to be sort of a distillation of all the lessons learned, mostly the hard way, by doing stupid things, and I'll try to impart them onto you. So just a very, very brief overview, because if I'm doing this right, we won't have time to cover all the things, so you have a rough idea of what's still in store, because at some points I'm going to ask whether you want me to drill deeper into something or you want me to move forward. So basically, the three main topics I'm going to cover are just some of the design constraints I think a good data science environment should have, and just about the process of doing data science. The second one is going to be talking about an environment for doing so. Here we're going to talk about mostly notebooks versus REPLs and how we can have more programmable environments. And the biggest chunk is just the tools. Here, one big part of this is dedicated to talking about design decisions behind my data science library called Huri, built in Clojure, and then some things about having feedback loops and the importance of feedback loops, and last but not least, how we can extend an ecosystem by building small compilers that target other language runtimes, such as building a small compiler to SciPy or to ggplot and so forth. Right, so before getting started, can I have a quick show of hands, how many of you already know Clojure? Okay, and how many of you have actually worked in Clojure? Okay, cool, thanks. So just, I can sort of adapt to the level, so I won't go too much into details about Clojure. Okay, so let's start with the design constraints. Now, the first thing is that this talk is very much targeted at working on a single machine. This is for two reasons. First of all, I think that most of our data cases can be done on machines, people from Google and Twitter notwithstanding, obviously. And the second reason is that even when not, we can often be smart about it beforehand and sort of do a divide and conquer of complexity and try to massage our data beforehand and turn into a shape where we can then work with it on a single machine, meaning just having a sample or having some form of pre-aggregation already done and then just work with this data on a single machine. And I think such a separation of concerns greatly increases developer productivity because I think it's quite horrific that there are now more and more notebook environments coming out where their main selling point is this seamless integration with Spark. Yes, this is a good way for some tasks, but very often you are approaching the whole thing wrong. You're just including massive additional complexity in form of sort of big data, kind of data pipelines where you should focusing on how I can shape my data in such a way that I can work with them on my computer. So here's the first sub-question. Do you want me to go more into details of how we prepare data in advance to make it more feasible to work on a single machine, or, and this is more kind of a DevOps thing, or should we go on with language design and actually working with data once you have it on your system?
Go on.
Language design. Okay, so we're skipping this. The process of how I think data science should be done is, I think the core thing is, at some point it's going to boil down to the question of communication. You can build as fantastic models, but if you can't communicate what they do and how they work, it usually won't work in the context of the whole company. So, and this is an area that's often, I think, overlooked. So I'm just going to briefly a couple of core points that I think data science system should cover. The first something that I've very optimistically termed the analytics chasm. I think they're kind of separate in terms of just the duration from posing a question to providing an answer with data. There are this kind of categorical differences. You can provide an answer in 2 minutes or less. This is the ideal because it means that in most situations when you're brainstorming something or just want something, you can immediately pull out the data, have an answer, and continue with that. Once you're at this stage, this means that you can actually, for me, at this point, a company becomes truly data-driven because then any decision can be supported by data. Obviously, that's not going to always be the case, but then the next kind of group or category is having answer done in 20 minutes or less. And obviously, the numbers are not super precise. It's just kind of like a guiding point. And here, the idea is that this is something that, again, you can squeeze into your day without having to allocate too much time to it. Again, the benefit here is if you go over this, it's something that needs to be budgeted in your time, and you're going to incur this huge delay in how long it's going to take from the question being posed to providing an answer. And this is a problem because then oftentimes what happens is that the question won't even be relevant or it's going to change or something like that, and it just, your results won't have as much impact as they could if you would provide it sooner. So a lot of things that I'm going to talk about are are optimized towards developer productivity in the sense that they allow us to provide fast answers to the questions that any stakeholder in company might pose. And then, yeah, just stop me anywhere in mid-sentence, no problem.
Are all analytics created equal? I've had to answer questions that have taken me half a day to write a query, even though we have all the data on hand, and I have the same data and I can produce an answer to a different question in 30 seconds. So it's every single thing's the same?
No, but I think that at the point where you have a problem that is a question of writing a single query which takes you half a day, that's a problem of tools. That's a problem of the expressibility of your language. And this is exactly the kind of problems which I would like to squeeze into the 2-minute gap. There are obviously some, and this is on your right side or whatever, of this timeline, the project size questions. There are sometimes you just don't have the right infrastructure in place, or you need to scrape some data or whatever. So those are obviously can't be solved in such a short time. But at the point where you have data in a relatively well-formed and stored in a database, I think that we should strive towards providing answers quickly. Now, obviously, the more machine learning you involve, the less this is possible, but front of analysis, this should be kind of the target frame. And exactly, basically, this question was perfect. Just, I hate spending half a day writing a long query. This is something that, in most cases, we shouldn't have to do. And I think that this is solved on 2 levels. One is in terms of just the tools we have, and the other is how much and how we prepare data in advance. So, and maybe just a quick then reverse level, though you didn't want me to talk about this, but one thing that, yeah.
The question is why Clojure should be different from the other languages like Python for the same thing?
Yeah. that's one of those where I was expecting the question. Fundamentally, we're using Clojure because I love Clojure. I've been a Lisp programmer for 12 years now, almost exclusively, and I picked Lisp when building up this department because I knew I was going to be most productive with it, and I knew I have a I know the path of how to make people fluent in Lisp in a relatively short time, so it wasn't a problem. So the staffing wasn't such a big concern. But most of the things I'm going to talk about here aren't exclusive to Clojure. I think that a lot of design decisions, I was influenced by the Clojure ideology, but I think that a lot of those can also be either directly translated to other languages, or at least the core insight can be transferred and used somewhere else. So we're using Clojure because I like Clojure, not because I think that Clojure is the ultimate language for doing data science. Like the Julia people are doing lovely things. It's a very interesting language to check out, and they're like also some of the things that they're doing numerically with Haskell are very interesting. So no, there is no reason for Clojure except it, or maybe the other reason is that it's also why I like Clojure is because it seems to resonate with the way I think. Now, in some ways, this might be that just using Lisp for so long has shaped how I think, but just thinking in terms of structure, and this is something I'm going to get into eventually, hopefully, is that it matches very well with how I think of problems and how I analyze problems. So I'm looking for languages which are very strong in terms of manipulating variously nested or complex data. Okay, so just.
How important to have immutability in the language?
I think it prevents a certain class of problems or bugs, which in turn aids faster development. As anyone who's worked with, for instance, pandas, you've probably got bitten at some point where they have this. Sometimes it's a copy and sometimes it's not. It's a mess. At least with Clojure, it's very unified in terms of performance. It works well enough as long as you're like most of the data sets I work with are around 1 million data points to 10 million data points, and all that stuff can be worked readily on my machine. So it's fast enough for the use cases that I have. I suppose that if you want to have absolute performance, you want to do more mutability, but even with Clojure, this is becoming less and less of a choice because, for instance, with introduction of transducers, which is kind of you can think of them sort of as a stream fusion in Clojure, but what they did is that behind the scenes, most of a lot of that is done with mutations. So you don't even have to choose, but this mutation is not exposed to the end user. So still, and I think that's kind of the best situation you can have, that language itself is not afraid to use mutation, but it's not something that should be readily exposed to the user. Okay, so just a quick note on preparing data in a readily way. I think that this can, in some ways, it might seem that I'm just kind of pushing the problem and sweeping the problem underneath a rug, but what we do is that we are very aggressive in just automatically building various views of our data. So what we do is we would have an ontology of our events and the attributes of those events going in, both a manual ontology and some of it inferred mostly from just the data types of the events. And then we build automatically various views for that. You can think of, like, for instance, every time that you'll see a date, we'll build various aggregations on a daily level, hourly level, monthly level, and so forth. And then we do seasonality detection, so we kind of have this rough idea of which kind of frequencies within time make sense to combine them, or whether you want to build a drill down, it doesn't matter. So you'll have readily available a lot of types of pre-aggregated data and not having to code for them explicitly. So every time a new data source comes in, we just basically classify it in terms of our ontology, and then we get a lot of things just for free. And this immensely helps with such a development cycle, because we then don't have to pay as much in terms of just preparing our data, and still it's readily available at any point that we want to use it. Right, so continue on. Now, in terms of environment, I was saying that it has to be visual enough that the main way of conveying information is through visualizations rather than through numbers, because there's way less information is lost that way, and it opens better new questions. You can very soon, you know, those problems with averages and stuff like that, and as the moment you're looking at the distribution, all of those problems just fall away. So you want an environment where visualization is encouraged as much as possible. Yeah.
For this type of visualizations, do you think it's better the REPL instead of the notebook style? So what do you think about it, and how this helps, Clojure helps about it?
Yeah.
I didn't like the presentation before.
I think, or let's start at the end. Ultimately, I think that a notebook is a better means for specifically doing data analysis, but it shouldn't be an either-or question. I think that both should be used together, because fundamentally what you gain with the notebook style of representation are two things. You gain spital grouping, and you gain more rich information. You can sort of incorporate more rich information easily than with REPL, although if you're using Emacs, that's kind of a moot point.
What is spital grouping?
Or I'll start with when the REPL is good, and this is the kind of inverse. With REPL, what you'll have usually is you type in one thing and after the other, so you have this completely ephemeral way of working with them. You're just adding new things, and even if you just have some throwaway code, it just stays somewhere there. And then you refer to something that you've done previously, and it's now lost into screens of REPL down the screen. So what the notebook, on the other hand, allows you is that you can group together similar functionality or similar analysis, even if you do it sometime later. So basically, a notebook allows you to structure your code more as you would in a textual file rather than how it looks like in a REPL session. Obviously you can just use a code file, but again, it's always a problem with what you do if you just have some snippets of code that you want to try out. So I think that ultimately the best solution is to have both. Your end result is going to be incorporated into a notebook, but while working, it sometimes makes sense to have a REPL also available. Otherwise, you're just constantly deleting various small crap when you're experimenting with things and looking at functionality, especially with languages which allow you various forms of self-describing and self-documentation. You'll be using that in REPL a lot, and it's not an output that you want to be included in your end analysis. And further, what a notebook or any such environment allows you, and this is why I'm also a big fan of notebooks, is that there is this kind of a seamless way between having a notebook and then turning to a dashboard. Because first you start with a notebook, and then what we do is we add this auto-refresh functionality where each day or each month or however you want to specify it, we recompute all the things in the notebook. So you never end up with stale data. That was one of the big problems that we always had before taking on this approach, was that you have this kind of some stale analysis, in the worst case, maybe written as an Excel sheet and sent over email, and then you'd have 5 different versions floating around with slightly different results, and nobody knows what the canonical version is. While having a single canonical point, which is a notebook, and then having it auto-refreshed, it's always going to be up to date. And it's oftentimes also works as a wonderful kind of a early warning mechanism that you've broken something, because the auto-refresh breaks and you know that you've done something wrong, and then you can track the changes that you did to your data scheme or whatever. And also, as I said, kind of having notebooks is just, in terms of current tooling, it allows you much better sharing, and also it's, in a lot of ways, it's easier to build things around them. You don't need to be either an Emacs hacker or Eclipse or whatever. So for instance, what we do is we just add a simple annotation plugin to our notebooks. And the other nice thing is, if we have a...
Can I ask you a question?
Yeah, of course.
How did you make the trade-off between commercial products like Tableau, and there's a few products you can use for this kind of stuff, and building yourself? What were the things you thought about? How did you take that decision?
The decision was based on 2 criteria. I think that kind of most of, at least for our needs, most of the commercial tools cover this kind of a middle ground where very simple things take too long to do, and you can't do very hard things. So just kind of okay for some of the medium stuff, and that just wasn't a good match in terms of what my department was doing and is still doing. So we still do a lot of very simple analysis, or we do quite complex things which you just can't really visualize. And so for instance, we do a lot of custom D3 visualization, stuff like that, and you just can't do that. You can't have that kind of a level of either interactivity or complexity in Tableau. On the other hand, doing something simple just takes too long. And here's just literally one line of code to get a decent enough visualization. So it just kind of didn't mix well with what we were doing. And it's also, I think, somewhat this question depends on what's your team composition. Personally, because my background is more on the programming side than on the data science or math side, so I approach this in other ways from an engineering perspective, and also then all the tools that we're building and how the team works reflects that. But probably the trade-off is going to be different if your data science department is primarily composed of people who are maths or science part first and engineering later. So I don't think that this is necessarily the right decision for everyone, but it definitely works well for us. And also, one of the strong key points that I want to get to is that once you have such an environment, and if, for instance, this notebook is as well written in Clojure, then what you can do is you can actually change your running environment at runtime. So what happens here is, and just as a brief overview for those who aren't fluent in Clojure, what we do is we extend the rendering of our output on the fly, and this rendering is then incorporated in the same notebook. So basically, we can use the same cells that we're using to do our analysis. We can also use them to program actually the environment in which it's executing. So we can add new types of visualizations on the fly if we want to, or something else. For this example here, concretely what it does is it just allows you to print infinite sequences and stops them at the first 10 elements. This is just a toy example, but the main point here is that if your execution environment is done, what I would say actually right, is that it's exposed enough that you can actually program it from within itself, that you don't have to have separate basically module system which you program like in IPython or something, but you can modify most or all of the functionality at runtime. This is, again, an idea for people who are from the either Lisp or Smalltalk tradition. This is nothing special, but I think it's, in terms of notebook environments, it's not a readily accepted idea, and I think that's a big shame, and a lot of gains will be made in the coming time with more people hopefully embracing this approach. Questions? Okay, so enough about environments for now. Let's maybe just right now what you've seen is, it's called Gorilla REPL. It's just some Clojure notebook, which is in a pretty bare bones state right now. So a lot of work here should also be at some point done with making it better and more powerful and featureful. But this is something that we're slowly also starting to open source some of the things we already have done internally, but I think just in terms of what the Clojure ecosystem offers here, it's kind of enough, but it's far from good. And still, even though I like having my notebook very programmable, I would still oftentimes love to have a much more mature environment, something like Jupyter or something. So here the situation is not ideal, but it's getting better.
What data processing libraries do you use?
That's the question you didn't want before. So what we do is, for data ingress, we stuff all our data into Kafka, and then we use Onyx to build various views in either PostgreSQL or Elasticsearch. And from that on, we're using the library I'm just going to start talking about to actually manipulate data. Right, so going back to this dichotomy I already talked about between a lot of people seeing data science as kind of either or between engineering and data science, I think that there shouldn't be such a clear delineation, and that this is in a lot of ways hampering the tools that we already have and the libraries that we already have. Now the core offender here probably is the data frame. And I know this is going to be somewhat controversial, but I think that oftentimes that's simply not the right abstraction. Why? Because it sort of conflates two things, representation and abstraction, and kind of forces you into this matrix-like way of working, which sometimes makes sense, but oftentimes, especially at the beginning stages of analysis and when you're cleaning up data, what you actually have is very heterogeneous data. And in those cases, data frame is a relatively poor abstraction of what you actually want to work with. And on the other hand, this is somewhat Clojure specific, as that Clojure excels in structure manipulation and kind of encoding computation into structures. And so it's a shame to move away from that. Yeah.
How much do you think it's the capability of Clojure to using immutable data? So there's a big difference between Python or R, big R, makes a difference in your work. Because you said it excels in the structure manipulating, no? So I mean from the just data, but it's just like another language like a big R.
I think that it's not so much about mutability per se or immutability, but it's a question of how you organize your problems. And I think that this is not just by being functional, what you usually tend to do in Clojure is you just have like a pipeline of transformations one top the other, and one's composing programs in such a way that actually it's not even natural to do mutations, because it's just kind of a transformation from one to the other to the next, and so you have no need in terms of thinking to do an explicit mutation, because I know sometimes there is a problem if you have a very pure language and just some algorithms don't hash very well together with not having any sense of mutations. But concretely for kind of analysis type of tasks and data cleaning, I think that's not the case, that most of it can be defined as kind of series of transformations, and so immutability is even less an issue. It saves you, as I said, from sometimes of bugs, and that's it, but it doesn't impose a cognitive burden on me. And also looking on some of the junior people on my team have never before programmed in a functional language. They have Python background and stuff like that, or MATLAB, and they don't have big problems with working around Clojure being mostly immutable. I think it's a very small step to kind of start thinking with immutability in mind, and then you completely forget about the immutable approach. And now back to this kind of encoding computation in structure. I think that's a very powerful idea, or at least that's kind of going back to when I was saying why I picked Clojure, because of how it kind of meshes with my thinking. And a lot of times for me, it's easier to think of the problem in terms of kind of various nested structures, one with the other, which encodes some step of the computation, and then basically doing at the end some reduction which turns the structure into a more normal or data frame-ish form, rather than being forced to, at all steps, having a transformation from a 2D data frame to a 2D data frame. So basically adding additional dimensions oftentimes makes, I think, problem more easy to think about, just in terms of how you want to approach it and solve it. And it also gives you, it also gives you niceties such as it's very easy to then encode something like a distribution, which can just be a map. If you have a discrete distribution, it's just a map between kind of keys and values, and get the distribution out of it. And that's a way more elegant way of representing that as kind of any alternatives you would have in a more data frame-oriented world.
Yes, and what about laziness? Is it something that also was an advantage?
Yeah, occasionally yes, because especially when you're working with relatively big data sets and you're on the edge of what your memory can handle. But at least in my working, it's not such a huge gain as you'd have in Haskell, for instance. I think also this is just due to the nature of language. Overall, in Clojure, laziness is nice. Sometimes it can allow you to express something elegantly, but for instance, if we want deferred evaluation, we're forced to use macros anyway, so you don't get those niceties. So, but and also, oftentimes what happens in Clojure is that even algorithms which are, or operations which are nominally lazy, you would then have them collapse into a non-lazy transducer operations, which are more efficient anyway. So you'd rather have stream fusion instead of just laziness. And again, so it's not as apparent as in maybe more hardcore functional languages. Okay, so back to our story and the tools that that's the library that I've built. So the idea is that I wanted something where which can be mixed together freely with the existing Clojure abstractions. So in Clojure, you have a lot of functions which operate on sequences, and I didn't want to lose this whole ecosystem, and there are also a lot of third-party functions, so forth. So again, this is another argument against data frames, that once, if you have a proper data frame, usually the rest of the language that's to do with working with sequences just doesn't work on that. So you have to either rebuild all the capabilities that are otherwise already present, or you're lacking things. So what I wanted is kind of an easy way to mix vanilla Clojure with my more data-oriented data-oriented functions. The other thing is that I'm very big on compressibility. This is composability, in some ways even going against what would be considered idiomatic Clojure. But again, I think that here, this is one of the, doing data science or working with data is one of the cases where sometimes it makes sense to go against what's considered best practice in terms of purely engineering side. This is again this dichotomy between doing data science and engineering, and sometimes you do have to make some concessions, and some things I would never write in a purely production code makes sense when doing exploratory analysis. So what my library does is that it offers most of the functions have current versions, which is not something that's always done in the Clojure ecosystem, because I think just composing functions together is a very powerful way, and this also gives you kind of this generalized accessors, because in Clojure also all the data structures can act such as functions. So it's basically, there's no difference between reaching within a data structure and then just applying some function to it. If you look at the example above, so what we do is first we reach into a data structure and pick the key of the slot called slot, and then we apply one function to it, and then apply a different function to it, and all this is basically acts as a unified accessor where we just kind of roll up then based on whether a day of the week is an odd or even number. And so you have this kind of what this kind of composition then introduces in a way is kind of this virtual structure where even though the you don't have a specific structure within the number, let's say 7, which is the day of the week, but if you apply another function to it, it kind of yields to this virtual structure. And this then provides a very unified way of working with various nested or otherwise complex structures. And that's something that I've grown to love, and most of my library is kind of designed towards with that in mind. Now maybe the last kind of, because we're compressed for time, the last thing I think that's kind of important or helps a lot is that still Clojure system, even though it can reach out to the whole Java system, is limited in terms of the libraries you have available, especially in terms of machine learning. So what we do is that we just kind of then farm it out to scikit-learn or whatever. We have small DSLs that compile to Python code and then use that. Because if you look at like something like SciPy, it has a very unified API, so it's super simple to just create the necessary Python code on the fly and send the data to it, read the data out from it or from a file or whatever, and then bring it back to Clojure. And then immediately you have access to the entire basically scientific Python ecosystem from within Clojure. And Clojure is very nice for that because as a Lisp, Lisps tend to work very well with building small and dirty compilers, and this is exactly such a case. The other example of that is that I'm using another DSL to generate ggplot plots. So you can here see relatively complex plots done in Clojure with very little code. So we have a small Clojure DSL, which then gets compiled to R, which produces an SVG, and then that's sent to the notebook. And you have a very expressive visual library available in Clojure with very little code.
Yeah, can you maybe tell us a bit more about interaction with other languages and the thing you were telling us before, especially in the live approach, in re-evaling from this, in this REPL and
Yeah, the examples you see here, for instance, calling out to R, this is happening on the fly. So basically, at the point where you evaluate, for instance, the bar chart invocation, what happens is that an R program is built from this description. It's sent to, it's basically an interactive R session is spawned. The result is an SVG, which is then taken as the output and inserted in the notebook. And you can do that, the same thing with scikit or whatever. So you just have to define some simple information interchange protocol, and that's it. And then it's the lag for something simple like using ggplot is negligible, and when you're doing some machine learning, the time that the algorithm actually runs is so much greater than the time to marshal information in and out that it just doesn't matter. And I think we're out of time. No? Oh. 1 minute.
There's 5 minutes of audience question time, so choose your own adventure.
A question to hypothesis you mentioned earlier. How do you integrate it with your notebook and with your workflow? Do you just use, I don't know how hypothesis works right now, because I supported it several years ago on Kickstarter, or was it Indiegogo? Is it ready to use for academic projects, for scientific projects?
We have our own instance running. Getting hypothesis running on your own is an endeavor. It's possible, but it's not something that you can just start up and you're going to work, but it's doable. Talking with the hypothesis guys, they intend to improve this thing a lot because they have a couple of use cases similar to ours and they want to support that further. But right now it's doable, but it's not very pleasant. So we have our own instance of hypothesis running, which is then, and the data that's stored in hypothesis is then also available to the rest of our systems, which then also helps with things such as discoverability. So what we do is we would write various either annotations or just tag things in hypothesis and then use that to make all of the analysis that we previously did, all the report and notebooks kind of discoverable. So when you have someone new, they can then just browse various topics and find out analysis that has to do with that, which helps with onboarding and sort of conserving all the knowledge that we've produced up to date.
For querying, are you using just regular Clojure functions or some kind of data log, some kind of more formal DSL or query language?
No, currently we're just using standard Clojure libraries, either for doing the SQL, just ODBC, thinly wrapped, and for Elasticsearch, we're using the Elasticsearch client in Clojure. But it's an area that I want to investigate more going to the future, is just various optimizations, because most of the times if you look at the structure of the code, it has this kind of very unified look. So it's basically using just the kind of pipeline, or like the thread in Clojure, well, this is the threading macro, starting with the arrow, and then you have various transformations one after the other. And that's something that could be very easily transformed into a more efficient form. So something, for instance, in common Lisp world, this is quite a common practice called compiler macros, where you have specific macros which catch various patterns in the code and transform them into something more efficient. And that's something I would like to do here as well, and then be able to, on the fly, delegate some of the computation to the database and some to the code. Because right now, just the workflow is that you basically pull the data from the database and then work it completely in Clojure, and then maybe at some point save it back. But it would make more sense and be more efficient if we could do more computation in the database, but at the same time, I don't want to sacrifice expressibility. So, but I think that there's a lot of low-hanging fruit that can be solved very simply with just looking at the structure of the code and then transforming that into the actual calls to the database.
Okay, so in your case, it looks like that you can handle data on your just one machine, on your machine only, no? But what about using Clojure with Hadoop or Spark? Do you think it's something that could be useful or achievable?
Of course, I mean, if you look, the Storm architecture, which was one of the first real-time processing systems, was written in Clojure and then bought by Twitter and used sometime internally in Twitter. Concretely, we're using Onyx, which is kind of a similar system, but also from what I gather, the story with working with Spark is very nice worded in Clojure, so definitely that's something that can be done, but as I said, we're trying to not use those systems too much in just doing day-to-day analysis. But like, if look at all the functions that marshal data around and either write to Kafka and read from Kafka and stuff like that, everywhere there in between, it tends to be Clojure, specifically Onyx, which then does all the calculations or aggregations or whatever you have.
One more question. You say that you think that Clojure, here I am.
Oh, sorry.
You say that Clojure is very good for expressing certain kinds of transformations. Can you give a concrete example for such a transformation that you would think would be harder to express in another language, say Python or so on?
There's also a trap here that I'm just going to show how ignorant I am of the capabilities of some other language. But what I think is that where Clojure shines most is when you have nested data structures, when you have something like a vector of maps that contain further maps or vectors or whatever, that's something like that, and you want to work with that. Here Clojure is very good and allows very concise code in how you then take that structure apart and build it back together. And I think the language is built with that in mind, so it also produces very idiomatic code. You don't have this kind of feeling that you're fighting against the language or it's kind of some horrible hack, but it's kind of just natural. And also I think what this produces is kind of this positive feedback loop where even if you look at Clojure programs in the wild and not even having to do with data analysis, you a lot of times see that they just encode things into various structures and then kind of work on that. So it's kind of a pattern that's pervasive through the Clojure world to kind of try to offload as much computation as you can into data structures. Okay, yeah, so it's kind of, hopefully this talk wasn't too chaotic. I didn't really have a good handle at how it's going to look, but yeah, just kind of to sum up what I think the main points I'd like to impress on you is that when doing data analysis, speed of answer matters because you're never doing data analysis in a vacuum, but you're doing it in a context of other stakeholders, and for them this matters. And second of all, it's about communication. So look for tools that allow you good communication, not just solving the problem, or rather, your problem is not just producing a number or a model, but it's also communicating that, and that oftentimes is left out. And we don't have to reinvent every wheel in Clojure or whatever language you want, Elm, Elixir, whatever. We oftentimes are very good, especially if you have a relatively powerful starting language, you can just build mini compilers and leverage other platforms, and this can be done surprisingly robustly and surprisingly concisely, and works rather well. And as we've talked a lot, I think that one of the core assets or strong points of Clojure is how good it is at working with structured data, and this is something that can be very nicely applied to problems in data science. Sometimes it might be forces you to switch in thinking from a very matrix-oriented view to a different kind of view, but I think that overall it aids in how fast you can just kind of imagine the solution and then obviously type it out. And last, and something that I would wish to spend more time on, or maybe in some other talk, is just kind of this idea of blurring the line between your development environment and the work you're actually doing, and how melding those two more together can yield a much better and much happier development experience, rather than having these two separate systems which don't really talk to each other. So thank you for your help, your questions.